So hi everyone, my name is Leonardo Militano and I'm a senior researcher at the Service Engineering Group at the University of Applied Science in Switzerland. The Service Engineering Group in Switzerland is its core expertise in infrastructure as a service, platform as a service, software as a service, and everything that is related to virtualization. And its focus is mainly on scalable and reliable implementation of IT-based services. We have several research initiatives, but the biggest one is probably cloud infrastructures and platforms and cloud native applications. And we're also active in cloud robotics solutions. In this particular presentation, I will be introducing some of our recent work we have made in using Alluxio for in-memory data computation. And specifically, the presentation is focusing on how to accelerate data computation on Ceph Objects. So I'll start sharing my screen now so that we can go through the slides. There you go. So the title of this presentation is Accelerating Data Computation on Ceph Objects. The agenda of this presentation is as follows. I will first introduce a bit of a context for this work, and in particular on the cloud storage area. And from there, I will be introducing some aspects of data analytics and solutions that are based on data locality in particular. And from there, we will move to our recent results and analysis we made on Alluxio-based solutions for in-memory data analytics, and present some results on the performance evaluation we have done in our lab. And at the end, I will draw some conclusions. So first of all, what is cloud storage about? I would like to introduce this, giving some numbers to set a bit of a context of where we are today with cloud storage. In particular, from the market perspective, the global storage market was in 2019 about $49 billion, and it's growing incredibly fast by 26%, and it will reach, according to Fortune Business Insights, it will reach about close to $300 billion as a market. At the same time, we are observing an increasing demand for data storage. And according to IDC, we expect this to grow from last year, so in 2019, 41 zettabytes to 175 zettabytes in 5 years from now, so in 2025. And in particular, what is interesting to observe in terms of where the data is stored is that 49%, so about half of the data will be stored in the public cloud environments. And this is very important, so that we observe that the public cloud is taking a large, is very important. But at the same time, we're observing also that not only the remote, the public cloud is important, but also we see a kind of a paradigm shift where more data is created, is stored and processed at the edge of the network. Not only the public cloud is important, but the edge of the network is gaining importance. And the last aspect I would like to underline in this introduction is a sentence I take from The Economist from 2017, where they stated that the world's most valuable resource is no longer oil, but it's data. And in particular, if we think at the biggest, largest companies like Google, Amazon, Facebook, Microsoft, and so on, they're all investing on how to exploit the data they are owning, the data they are storing for the customers to generate some additional revenue. So if we think as the data as the new oil for the 21st century, then this brings me to the next aspect, which is data analytics. So in particular, if we have data as the new oil, we need to process this data, this raw data, into higher order products so that we can benefit of its actual value. And what the value is the information it contains. And we can imagine if with the huge amount of data which is stored in the cloud and also in the edge of the networks, as we saw, it is very important how we are processing the data to extract the information we want to. This leads to the next point I want to introduce is how the storage and the computation elements are actually collaborating and how they work together. The typical approach that we have observed over recently is that disaggregation of storage and compute is promoted, and the motivation for this is that it is efficient in terms of costs, but it's also making the manageability of both of the two elements easier. What is the consequence of having the storage element and the computation element disaggregated from each other? The consequence is that the data is remote from the compute nodes. This means that if we have to extract some information from raw data, if we have to do some data analytics on the data we are storing, we have first to move the data, the raw data, from the storage cluster to a computation cluster, and there perform some data analytics before pushing back the results on the storage. This has an effect on several performance indicators, and in particular, if we think at the network that is connecting the two elements, so the storage and the computation clusters, this is we are sending data over not only over the core network, but also in the network access, which typically is a wireless access. So it has an impact on the bandwidth we are using. At the same time, it has an impact on a higher power consumption, higher costs, and also higher latency, and at the same time also security, because you are sending your own data, the raw data, over a network. So what we observed in our research activities is that probably in some cases, in some use cases, it's probably interesting to find some alternatives to this. And two of those that we have been investigating are on one side to bring the code closer to the data, and in this area, one particular technology that is taking place, gaining interest, is computational storage, which means that the storage devices themselves that are storing the data are enhanced with some computational power, so that we can, in a way, bring the code to the data and do the data analytics directly where the data is stored, without having to move the data from the storage to the computation. And on the other side, the other hand, we have another approach, which would be to bring the data closer to the code. And here we think in all solutions like caching, but also in memory computation. So what they have in common, these two approaches, is that we have data locality, and data locality has several benefits and brings several benefits exactly on those performance indicators I was mentioning before. So bandwidth, power consumption, cost, latency, and security, because the data is close to the computation element, where the data analytics happens, and so we don't have to move the data back and forth. So we have performed some analysis on both of these aspects. In particular, in our lab, we have experience on Ceph, among other storage frameworks. But Ceph is a very interesting, very established solution as a unified distributed storage system, which has a lot of nice features. Among them, we have self-management and healing. And the very nice thing of Ceph is offering the whole spectrum of storage solutions, so object, block, and file storage. And in particular on Ceph, we have done in the past some analysis on how the solution where bringing the code to the data is performing. In particular, we have investigated how so-called Ceph object classes to do computation directly on the storage devices is showing very high time savings when we compare to the situation where you have to fetch the data from the remote Ceph storage cluster and move it to a computation cluster and do the computation there. So we have done we have found some nice results there. And then we wanted recently also to investigate the other approach, which means bringing the data close to the code. And we found, or we got to know Alluxio, which is a solution for compute nodes to allow them for memory speed computation. So the nice thing that we found out is that Alluxio also has support as a backend Ceph storage. So we took the chance to bring these two elements together and to analyze how to bring data close to the code is working, how it is performing using Alluxio and Ceph. So in the next slides, I will present what we set up as a framework for testing this solution. In particular, you see here in the slide, in the picture in the slide, we have a storage cluster, a very simple one that we had in our lab, we set up in our lab. It's based on Ceph with 6 VMs, where we have one virtual machine that is for Ceph monitors, 3 objects, 3 OSDs, 1 Rados gateway, and 1 administration node. The total storage amount was limited, but was good for our scope. So it was 420 gigabytes, and it was distributed over 7 volumes. On the other hand, we set up a compute cluster, and this was based on Alluxio. So in particular, we had set up an Alluxio compute cluster using, in first instance, version 2.3 of Alluxio. And later on, we also tested, as we will see in the performance evaluation, version 2.4 of Alluxio. On top of this, Spark Apache was installed, and on top where an application was running a Scala application, a very simple Scala application that was good for our scope. In particular, it was an application that was accessing a text file and counting the lines of the file. In particular, what specifically was of interest for us is how it is performing when you have repeated access to the same file. In particular, this is important to mention because in this case, we found out that Alluxio really brings some benefits. So if we repeatedly access the same file and repeatedly do the same analytics. So we set up 2 different configurations for the Alluxio cluster. The first one is a very simple one with a single node, 1 VM that has 16 virtual CPUs for Alluxio and Spark, and 40 gigabytes of memory for the worker node. And later on, we extended it a bit more with 2 additional nodes with the same configuration. I will not dig too much into the details of this. You find more details on our blog post of our university. But we use this setup, these 2 cluster configurations to make a comparison in terms of overall execution time for our computation, for our data analytics solution. In particular, we're comparing an Alluxio-based solution versus a direct Ceph access. So when you want to fetch a text file directly from the backend storage Ceph or going through Alluxio. Here we compare 3 different file sizes, in particular 1, 5, and 10 gigabyte. And what was the focus of our analysis is to see how it behaves when you have a repeated access. So you repeatedly access the same file and count the lines of the text file. And also what happens if you restart the whole setup, whole application, if you restart Spark and Alluxio and so forth. What we'll present now is the performance evaluation in our cluster configurations. In particular, the first slide here is showing, histogram is showing the single VM setup results. On the x-axis, as I said, we have the file size. On the y-axis, we have the execution time, which means in counting fetching the data and counting the lines in a text file. Let us start from the yellow and the green bars. These are the bars that are referring to direct access to the Ceph backend storage through Spark. In particular, the yellow one is the first time you start application, and the green one is when you restart application. As we see, we don't see between the yellow and the green bars, there is no major difference. And this is exactly what we expect because there is no reason this should change. You are restarting the application and accessing the backend storage for an object. Either you do it the first time or the second time, nothing should change. Of course, at the time, absolute time increases with the file size. What is particularly interesting is what happens with Alluxio. If you, we can start from the blue bars, and the blue bar what we are doing is the first time you request Alluxio for a text file that is stored on the backend Ceph storage, it will go to the backend storage, fetch the data, store it in memory of Alluxio, and then execute our data analytics. So as we see, it is in the range of the execution time of the yellow and the green bars. This is expected. It is a bit higher, and the motivation for this is that this data has to be stored on the memory of Alluxio. But what is really interesting is to observe what happens when we have a second access. So if we look, for instance, at the first set of results, so for 1 gigabyte of file, the blue bar in the second access, which means the second time we request the same data text file and the application is counting the lines, we see a drastic reduced amount of time it takes. And this is valid for all the file sizes. And what is also very interesting is to observe the red bars. The red bars are showing what happens when you restart the Spark, you restart the Alluxio, you restart everything. And also in this case, the red bars is showing very low values of time. The motivation for this is very easy and very clear. The motivation is that the second time you access the text file, and also when you restart the application, the text file we were accessing was already stored in the memory of Alluxio. So it didn't have to go back to the backend storage of Ceph, which is remote, but it could execute directly the analytics you wanted to do. This is a very important result. In the next slide, we are showing instead cluster setup results. So I remind here that we have 3 nodes now. The first effect of this, what we can observe, is that the execution times in the cluster setup are reduced for all cases. And this is obvious. We have 3 nodes working now instead of 1. And if you look now, the maximal value we reach is 400 seconds. In the previous setup, we had up to 1300 seconds. And the behavior of the bars, the behavior of the solutions is similar. In all cases, we have that Ceph, when you do direct access to Ceph, also when you restart the application, also in the second access, there is no major difference. And this is what we expect. But at the same time, when we use Alluxio, the second time we access the same file and do the computation. Also, when we restart applications, so referring to the red bars, there is a huge benefit of doing this because we have a very high gain in terms of execution time. What we observe as well is that since the absolute values in all cases are reduced because it's performing better, the gain itself is reduced. So commenting and summarizing the results we have obtained in our analysis is that in the single node setup and in the cluster mode setup, we have important gains. In the single node setup, we range from 75 times to 111 times faster data analytics. So using Alluxio compared to direct Ceph access. And of course, this ranges between, according to the file size, so the amount of data it has to fetch from the remote access. In the cluster mode setup, still we have very important gains. It ranges from between 35 and 65 times, which is very nice. But here now comes an observation of our results. All the results I have shown so far, all the tests I have presented, are based on the setup where Java version 8 is used. The motivation for this is that this is a prerequisite of Alluxio version 2.3. So Alluxio version 2.3 needed Java version 8 to work. By chance, in a way, we discovered something interesting, interesting result, because when we set up a new cluster with Spark, accessing directly the backend storage, so the accessing directly Ceph, by default, when you install Java, the default version is now Java 11. And we observed that Spark, or the application, was performing much better. In particular, if we observe the absolute values, there was actually no gain anymore in using Alluxio. This made us think, and we found out that Alluxio version 2.4 was coming out. We were able to test it even before it was released in October of this year. And the very important thing is that Alluxio version 2.4 was supporting Java 11. So we repeated the whole setup. We repeated the all analysis we did before with version 2.4. And in particular, what I present here in the slides are the results for the cluster setup. Here again, we see a similar behavior. Of course, what happens now is, since we are using Java 11, the performance in all cases is much better. And we see here that it's the maximum value is about 85 seconds, which is way less than what we saw before. So since the whole system is performing much better, the gains are somewhat reduced. But still, in the second axis in particular, if we look, for instance, both in first set of solutions for 1 gigabyte of file, but also in other ones, we see that the blue bar and the red bar in the second axis are lower. So there is time reduction in execution time. So this brings me to the conclusions of our analysis and of this presentation as well. What we can conclude is that Alluxio in general enables memory speed data access by eliminating remote data reads, and which is particularly important according to our results for repeated access. So when you repeat the same data analytics, you repeat the same access to the data multiple times, then there Alluxio from our results was very important, introducing very important benefits. And these are violated both in the single node, but also in the cluster mode setups, leading to several orders of improvements. The next conclusion we can take is that Alluxio 2.3 had the Java version 8 as a prerequisite, which was a kind of a limiting factor, which was removed then by Alluxio, which is removed by Alluxio 2.4, which supports Java 11. And this is fundamental to keep the performance improvements with respect to direct backend storage access. This concludes my talk. Thank you very much for your attention. In this slide, you see also my email contacts. Please reach out for any questions or comment or any possible also collaboration with us on this topic. Thank you very much.